In this video, we're going to look at systems and free body diagrams, and this is the main way that we'll represent forces in this unit. So free body diagrams, before we talk about them too much, we want to talk about systems. A system is a collection of objects or things, if you want to be a little more broad. And when we're talking about systems, we're typically only looking at external forces. So what do I mean by this? Well, if you think about like your hand, and what makes up your hand, well, there's 5 fingers on your hand. Each of those fingers is made up of a bunch of cells, is made up of a bunch of atoms, and we can go down to all these different levels. So there's all these pieces that make up my hand, but if I treat the system as my hand, I don't care about all the forces between those, because as we'll see later, all the internal forces of a system cancel out by definition. So it's only like when I have something come along and push against my hand that I start to care about, like, if my hand pushes against something, I only care about the objects or the forces outside of my hand. So how do we make a free body diagram, or what is a free body diagram? It illustrates all the forces acting on, and this is critical, a single object. So you can only ever do a free body diagram for a single object at a time. Now you can do multiple free body diagrams to illustrate what's happening to multiple objects, but each diagram is for one object. So the way that we do this is we draw a dot to represent our object. So over here I'll draw my dot. So let's say, it's a book sitting on a table. We draw a dot. Then we illustrate all, sorry, one second. We illustrate all vector, or all forces as vectors. And specifically vector arrows. So all forces are depicted as arrows. The arrows begin at the dot and extend outwards. So you always start on the dot and go out. And then the length should be proportional to the magnitude. So if you have a force that's twice as big, it should generally be drawn as twice as long. So again, for that example of the book sitting on the table, you don't need to know what these labels mean or how I need to draw them for now. But there's going to be some upward, what we call normal force. And then there's going to be some downward, what we call gravitational force. Now from Newton's first law, if the book is sitting on the table, we know all the forces have to be balanced. The net force has to be 0. So that means that these should be roughly the same length. And in fact, they are. So another example of a free body diagram is maybe there's this toy that's being pulled on by a bunch of dogs. So we might have the force of dog 1 pulling this way, the force of dog 2 pulling that way, and the force of dog 3 should be actually not pulling like that. It should be more pulling like this. And if these could all be balanced out. We don't know. We'd have to add them up to see, but we can see we've put 3 on here. And let's give another example of, if I have a rocket ship, it might have the force of gravity pulling it down, and then this big thrust force, or like rocket force, propelling it upwards. So in this case, we would expect to see an acceleration, because there is a non-zero net force.